This is the first time here in this school, even if Muriel tried to invite me long time ago, but it generally is a difficult moment for the academic year, but this time I was free and so I cannot refuse. We'll do like the students, 90 seconds to present myself, and I know myself, so it will take probably 900 seconds, but let's go. So my academic journey around the globe. So I born and raised in Rome, Italy. I born 2 years after the construction of the Berlin Wall. You will understand why I'm making reference to the Berlin Wall. And I obtained my bachelor in geology at the Rome University. And I make my master in geology in soil gas geochemistry and apply to geothermal resources. And this 2 days after the fall of the Berlin Wall. So that make me believe that when I do great things in my career, greatest things happen around the globe. So you will see in 5 years when I retire what will happen, maybe in Russia or other place. I moved in PhD with Bernard Marty in Paris 6 University at the times. Now everything is called La Sorbonne. In noble gas geochemistry, I was the only guy that decided to do noble gases in the darkest things that exist on the planet, petroleum, to understand the petroleum movement in the Paris Basin. And then I decided to go in postdoc at the Osaka University, and then I start to work in astrobiology. So I arrived there with a project to do noble gas to trace paleoatmosphere in '95, but at that time nobody believed that you can find a paleoatmosphere trace in all rocks of 3.5 billion years. But I have a chance to meet somebody who was working on nitrogen isotopes in meteorites, and so I wrote a series of seminal papers on the Archean biogeochemical cycle of nitrogen. We will see this in a slide. Then I go back in Paris 11. I became a maître de conférence, that is a position between slavery and assistant professor in the French university system. And I continue to work in arc environment, in nitrogen and carbon isotopes. And then in 2004, I decided to move. I quit astrobiology. I will explain at the end of this presentation this morning why. And I move in the University of Quebec in Montreal, when I became professor, and since 10 years I'm director of Geotop, that is one of the biggest research centers in geoscience in Canada, and doing noble gas geochemistry again in fluids, and we will see other. So I can resume my research in astrobiology with these figures that I modified. That it's here you can see the nitrogen and the carbon isotopic composition measured in rocks, in charts. You saw this kind of chart probably yesterday with a sample of Jean-François Moyen. And we see a shift between Archean and Proterozoic, so let's say rocks around 3.5 to 2.5 billion years, younger than 2.5 billion years. And I propose that, of course, these values represent a biogeochemical cycle of nitrogen where it's controlled by nitrogen fixation, nitrates, and denitrification. It's the classic biogeochemical cycle that you have in the oceans also today, because they were oxygen, so you have nitrates. But in the Archean, you don't have oxygen. We will discuss then when I will discuss about atmosphere. And so I suggested that the chemolithoautotroph, I forget completely this stuff, so biologist is sorry, probably fix mantle nitrogen around the hydrothermal chimney, and so the life was there, and the cycle of nitrogen was completely different. And then, as I said, I move on. I did other stuff, so I'm working in exotic place now in geothermal resources. So very beautiful place, like here in Krapla in northeast Iceland, in Argentina, Patagonia, or here again Testerikir in Iceland, or in the Cuchillo National Park next to Lama stratovolcano in Chile. I do a lot of stuff. I'm dating groundwater. I try to understand how form diamonds in the mantle, the behavior of metals in geothermal fluids. And this I'm very proud because I have some implication for astrobiology. Nobody knows what is the bromine isotopic composition in the mantle, so I tried to measure that using a different approach. And so I proposed this paper with the bromine and chlorine isotopic fractionation in the mantle that is fractionate to compare the chondritic to expected value. And since this fractionation is a memory of the moon giant impact that created our satellites. Unfortunately, this paper appeared the 14th of March on 2020, when the North America closed because Europeans sent us a strange virus. And so I think is the less read volume of Geochimica Cosmochimica Acta since its start of publication. So unfortunately, sometimes you do not control what is going on. But we are here to discuss about primitive Earth or young Earth. So first, because I think there is only one or two geologists here. And the most dangerous one, Jean-François Moyen, is busy because he will contradict everything I will present today. I will make a short geology course for dummies, including me, that I'm probably the dummiest one here. And we are speaking our young Earth or primitive Earth, what is meaning. And I will divide mostly in three parts. I will speak about the geosphere, and mostly particularly of the appearance of the plate tectonics. So how we move from a Stanian lead to plate tectonics, and citing one of my predecessor, Italian Galileo Galilei, and yet it moves. And then we will discuss about primary, secondary, and the habitable atmosphere. And then finally, because if not, Muriel will be not happy, about oceans. So I will discuss of the main reservoir of our planets. So this is the planet now, our planet now. As you know, we have a core, a metallic core, inner one solid, a liquid one external. The internal one made of nickel and iron, the external one of iron and some light elements. If not, the density calculations doesn't work. And so probably sulfur that is liquid and is producing this magnetic field that is the first most important things if you want to have life in these planets, because it's created magnetosphere that is a shield against the solar wind charged particle from the sun and the ultraviolet. So we are here for this reason. There are no green men on the Mars because Mars lost its magnetic field around 3.5 billion years ago. And then you have the mantle here. The mantle is made of silicate rich in magnesium and iron. Today, the upper part of the mantle is at 1,200 degrees around. It creates convection movement, but it's a solid. You don't have to expect that it is a liquid like the magma you see coming out from the volcano. Of course, it's not rigid. It's plastic, so you have this convection cell. As yesterday, Dr. Alveg said, when you boil water, you create this kind, because we're losing heat from the planets, and so we are creating big convection cell that cover all the mantle. And then you have the crust. You have two types of crust. The oceanic crust, that is the majority of our surface, 70%, that is made again practically the same material of the mantle, is magnesium iron rich silicates that is called basalt, these black rocks that you see when there is eruption in Hawaii. And so it's 5 kilometers thick normally. And then you have the continental crust that is an evolution of this kind of rocks. So it's less dense and is made of aluminum, potassium rich, sodium rich silicates. So if another chemical composition, less dense, more evolved, and everything comes from the mantle. So you take a magma blob, you have what we call the differentiation. That is not the planetary differentiation, it's magmatic differentiation. And you precipitate some minerals and you have residual liquids. And the liquids become more and more changing chemistry, more rich in silica. And so these rocks we call is mafic rocks. So it's really primitive rocks containing magnesium and iron minerals and poor in silica. And this we call felsic rocks that are rich in silica and contain these other elements like potassium, etc. And this contrast density is important because it's one part of the ingredient for plate tectonics. We'll arrive in a few moments. So then you have an ocean that is made of water, of course, an atmosphere then today is dominated by nitrogen, oxygen, and you have a little bit of argon, CO2 that is increased because we are polluting the planet, etc. We will see this a little bit later. The most important things for us geologists that we create an hypothesis in the last 30 years is a theory. So the theory is there to be confirmed or disfirmed. That is plate tectonics. So this convection is moving the crust and fragmenting the crust in plates for the reason we call plate tectonics. And we have construction of these plates at what we call the mid-ocean ridge. That is a place where the mantle come to the surface and create oceanic crust. And then we have another important processes that is subduction. This crust is recycled back in the mantle because it's pulled down inside the mantle. And we will discuss a lot of subduction because a lot of people, when they speak about when plate tectonics start, they mean when subduction, at least modern subduction is start. Because we have to define what we mean for plate tectonics to decide when start really on our planets. And this is not only, this movement do not only create a subduction, but you have collision between plates and construction of orogens, that means mountains, and you have widespread volcanism around the planets. Plate tectonics seems important because in any paper you read, from comets to atmosphere, at the end there is the classic sentence, and thanks to the plate tectonics, everything is put in order, and then we have life on this planet. It is a really important plate tectonics for life, and how we could have play for life. Here is a schematic. So if you have two convective cells, they are diverging. You are the plates are sufficiently viscous and cold to react to this movement, and so you break this plate and you create what we call the rift. Is a continental rift, or what we call the mid-ocean ridge in the middle of the oceans. So the mantle come up and the basalt form and the push again to the side these plates, and then you can have an area where you have two converging convective cells, and now you have one plate that is colder and denser that start to subduct so go under the other plates that often is a lighter one that is a continental crust. So the plates is floating on the mantle that is like your mattress, is plastic for isostasy. And so this is the reason why the continents have higher altitude, and of course the oceanic crust that is denser is lower altitudes. And the secret of plate tectonics for having subduction is not only this convection movement, but also you need a plate that is sufficiently cold that when it starts to subduct, the gravity itself is pushing down the plate. So you have at least two important forces, the convection and the gravity that push down. If it's too buoyant and hot and warm, like it was in the Archean, you don't arrive not to have subduction and not to have this plate that with the gravity is pushing itself down, up, down, mostly to the frontier with the metallic core. And so this is very important. But why it should be important, the people say, is the secret why we have life here and on the other two planets, Venus and Mars, because we have plate tectonics. What they do, the plate tectonics? So plate tectonics help to creating continents. So there are different ways to create continents. I will show you what we think it was the first continent. It was not built like the Cadinian craton here represented. but the classic model for creating a continental crust today is by a series of subduction. During subduction, you have the construction of volcanic arcs, like is Japan. And these volcanic arcs is, we say, accreting each other. So you have a collision, and when the plates go down, the terrains that are on the tops is piling up against the volcanic arc. So we call this accreting terrains. And you have a series of accreting terrains following different subduction. You are piece by piece connecting part of volcanic arcs, orogenics, etc. So crust, and you create a continent. And this very simplistic model born looking the North American cratons, where here you have by colors ages, Archean, very old. Yesterday, some people see and touch the oldest rocks on the Earth, the Acasta gneiss. Acasta gneiss is around here, is 300 kilometers north of Yellowknife. That is a town that born because you have kimberlite and diamonds there. Around the Slave Lakes, that is probably the same surface, or twice the Aquitaine regions, is enormous lakes, one of the 10 biggest lakes in the world. And so it lost nowhere. And this is the Archean core of the continent. And when you move centrifugally from the center to the border, you have more and more younger, you see stripes of terrains of Proterozoic, of Paleozoic, etc. So 3 billion years, 1 billion, 2 billion years, 1 billion years, 500 million years, and Appalachian origins 400 million years. So it's younger and younger because probably this continent has been piled up, starting from a core in this way. So adding terrains that one after the other, at different age, it's accreting and increasing the size of this that is the biggest and oldest craton on the Earth, but unfortunately is the less astrobiologically studied cratons. Because probably it's the fault is of the Canadian community that didn't respond as should have to the astrobiology effort as the Australians or South Africans did. Okay? So they do another thing very important. It helps to exchange matter between the outside of the planet and inside. Energy, heat. So we are losing heat since 4.5 billion years through this system of mid-ocean ridge, for example, and subduction can bring you back water or other elements, and other elements arrive at the surface. The most of the metals come from the mantle. Halogens come from the mantle. Has been brought by chondrite, like our atmospheres on our oceans. We will discuss this later. And we need theoretically plate tectonics and very early if we want to destroy our initial Venus-like N2 CO2 massive atmosphere we had on these planets. So we have something, a runaway greenhouse atmosphere like probably Venus, and this planet was able to absorb and put inside back to the mantle this gas. Venus cannot. And so Venus is leaving what we know, 400 degrees under his surface. The Earth arrived to habitable, not for us, for extremophiles, temperature relatively quickly. A way to do this is that you can, this is a sketch that is in one of the books that this mermaid asked me to write. And forget how much the amount of CO2. Initial CO2 was probably 1,000 bars in the atmosphere. But a way to eliminate CO2 from the surface of the Earth is to alter the crust at that period. The Earth. I take off the age because the people fix always on the age. It's somewhere between 4.5 and 4 billion years ago. Okay, I give a 500 million years error. That for us, the geologists, is just 1 second, so it's not really important. And what happened here, that the crust, it was like the moon. It was just basaltic crust, like the lunar mare basalt, etc. And if you alter the basalt, the weathering of basalt produces carbonates, and the carbonates can be recycling down through subduction. Is what's happened today. The most of the carbon going down in the subduction area today is in form of carbonates. But it means that this plate tectonics should work 4 billion years ago or 4.4 billion years ago. And now plate tectonics, like we know today, it didn't work at all at that time. And so we had to understand how we can recycle a massive atmosphere. So we need a killer for this kind of massive atmosphere to arrive to an habitable world very, very quickly. But let's take one step at a time. Let's go back to the primitive of young Earth vision. Effectively, we should speak more of a young planet than a primitive one, because it was not so primitive in terms of geological term. It was maybe in the first life form. And when I was a student, I remember we have this discussion often with Hervé Martin. We were both younger. This was the vision of the planet Earth. It was a hell. It was like a magmatic oceans covering the surface. It was toxic gases. Anything was happening. It was too hot and too hostile to have life. Today we have these other visions of the Earth with a craterized, probably basaltic crust with oceans, volcanism, probably an atmosphere, etc. Which one is true? It's probably both, because it's depending from the time frame that you choose. This was the planet at the end of the accretion, or very close to the end of the accretion. So we are speaking here now of planetary accretion, not tectonic plates accretion. So we have no magnetic field just because everything was mixed up, metals and the silicates. We have a magma oceans, probably around 2000 Kelvin. This is what is calculated for the moon, so we can expect more or less the same for the magmatic oceans. Maybe a reduced atmosphere. This is interesting for life, but we will go back to that later. I put here a time frame of 0 plus 50 million years, because 50 million years is more or less the times that the magma oceans survive on the moon. But there are models on the Earth that say that maybe the magma oceans in the Earth has been destroyed maybe or disappear in 1 million years. So we don't know. So let's put a maximum. Again, for me as a geologist, 50 million years is like 1 second error, so it's okay. On the right, so no interest in life, just because at 2000 Kelvin nobody can survive, even astrobiologists. So the right one is probably favorable to life. I put a time of 0 plus 150 million years, the famous Jekyll zircon. I go back about that. I don't want to speak much about this zircon, because with this zircon we said everything, even there were pink elephant living on the primitive Earth, so maybe we said a little, speculate a little too much, but there are important pieces of evidence. We have a metallic core, so we have a magnetic field. This is very important to avoid the ultraviolets, even if we know that we have extremophiles that live in nuclear stations, so they can survive this kind of radiation. We have oceans probably, or at least liquid water was stabilized at the surface at the condition of that period. We have a warm, buoyant basaltic crust. We have volcanism, and probably we have an oxide atmosphere made of CO2 and 2, and of course we have water in the oceans. I could put a time frame much later, because some people say that the metallic core has been, so the differentiation of the planets happened 300 million years after. There are new data with new isotopes that say they take only 50 million years. So again, it's very difficult to give an age here. And we have a hotter mantle. The mantle was much hotter than today. So today we say it is around 1,200. It was 1,600. And this is explained by this rock that is really not nice because it should be cut and will be fantastic. This is what we call the comatite. Comatite you cannot find today on the Earth. There is only one place, Gorgona Island, where you have a mantle plumes. I forget, but here I didn't. I will speak after of these strange things. From the frontier of the metallic core, we have a zone of turbulence where sometimes hot materials come up to the surface. Is what we call the mantle plumes. And so probably mantle plumes form this, and in places they are much more hotter, but it was a common magmatic rocks at that time. And what is nice, if you cut, it's difficult to see here, you have minerals very elongated. Is olivine and pyroxene is the first mineral you form when you cool down magma, and this you cannot form today because the mantle is not at the same condition of the redox condition and the temperature condition to form these rocks. So there is no equivalent except in this island of comatite. So we know that the mantle was much more hotter. And this is a very important thing when we will discuss about plate tectonics. Warm, buoyant basaltic crust and hotter mantle. So can we do with this warm environment really have subduction of plate tectonics? But let's look in detail this environment. So I will start with the geosphere, then I will move to atmosphere, and really last I will discuss the ocean. So I will keep this mermaid nervous up to the end. So let's speak about the geosphere. Unfortunately, we don't have two suns like on Dune, and so we have only one sun. The other never ignites, so it was the Jupiter, because probably divided his mass with Saturn, and so not sufficiently dense to form a second star. So the first question, when we look planetary interior of our planet, it's did early Earth have a plate tectonic regime as today? Today you can notice immediately that we have plate tectonics because at the frontier of these plates that are moving on the surface. So every year when I came here in France, my flight of Air Canada have to do 5 centimeters more longer the trip because the North Atlantic is opening at the 5 centimeters. So North America and Europe is become 5 centimeters longer. This is probably why the price of flight is more expensive now. And when I go in Japan, it's 11 centimeters, 12 centimeters, because we have another ridge that is the East Pacific rise, that is the most rapid one. So at this frontier of the plate, we notice immediately that we have something like plate tectonics because we have three phenomena that is very common. We have earthquake, like here in Kobe in '95. This is not my car, fortunately. Volcanism, like here in the Copahue volcano is in Patagonia and erupting. Or like here in Northeast Iceland, this is my student, Brazilian, Julia, that she tried to jump back to North America because where is this camping car is Europe, but at this other side is North America. So this is the ridge that is on the continent in Iceland. So if you want to visit a middle oceanic ridge, you have to go in Iceland because in Iceland is on the surface. So this is a classic way to see in our planet if we have plate tectonics. So this is produced by the tension between opening and closing, diverging and converging plates. Is the plate tectonics typical in solar system? And so we have in other planets. We could be tempted to say yes, because we have quakes even in the most immobile satellite like Moon, but the moonquakes is not produced by plate tectonics. Surface moonquakes is produced by meteoritic impact. Deep quakes in the Moon is produced by tidal force. So Moon produce tides on our oceans, but the Earth that is bigger produce planetary tides, and so the stress of the attraction, gravity attraction of the Earth produce earthquake inside the Moon, so nothing to do with plate tectonics. But then the looks at the Io and the Mars. Mars have this beautiful Yesterday, our colleague showed us how is deep and large Valle Marineris. It's a rift of 4,500 kilometers. And here in the Tarsis region, you have the biggest sheet volcano on the solar system, Olympus Mons, and this series of volcanoes here align. This rift and volcanoes, but this also is not produced by plate tectonics, as been yesterday said correctly. And then we have a widespread volcanism on this satellite of Jupiter, and this is the Italian astronomer when was the flyby of Galileo. They call immediately the pizza satellite, because for us it looks like pizza with tomato and mozzarella. And this again, this volcanism is not produced by plate tectonics. In fact, we don't have a plate tectonics except the Earth and Europa and Enceladus, but that is controlled by ice plates and the ice tectonics, so it's a completely different story, so I will not speak about these two satellites. Probably who is working on that know much better than me what is going on these two satellites. So indeed, in the solar system, we have what we call the Stanian lead. Compare the mobile lead that is the tectonics, or also called plate tectonics, we have on our planet. I don't like the name Stanian lead. So the Stanian lead is that you have a sufficiently thick, cold, and viscous lithosphere. So I have to explain what is the lithosphere. The lithosphere is not just the planetary crust. Is the first 100 on our planet, 100 kilometers of the crust and the mantle, where the mantle have a rheological behavior like the crust, is rigid. So it's like you have a rigid plate that react in the same way under tectonic forces. So this is the lithosphere, and so called a lead that is so thick and viscous that is not moving with the convective cell. The convective cell is moving and mixing the mantle, this plastic mantle that is not liquid, but the plate is stagnant. In reality, a real stagnant that is not moving plate is only on Moon and the Mercury for two regions, is dead planets, so you don't have even any more convective cells inside the planetary interior. So this is graphics that come from a publication of Stern. If you want to know everything about the Stanian lead and the old plate tectonics, you go on this number of special issues of Geoscience Frontier. I take several sketches from that volume. This is the lithospheric thickness from nothing to more than 1,000 kilometers, like on the Mercury or in the Moon. Very early hot, became warmer, and then later very cold. And this is the different stage of the Stanian lead. Very early one, intermediate, and the late one. If you look at the three most important telluric planets, Venus, Mars, and the Earth, were at the start, and there are still these two, an intermediate stage of Stanian lead. Is becoming more and more thick and viscous and cold, but still not like these other two planets or satellites. And still you have some tectonic force that produce volcanism or rifts like Valle Marineris. And so we have heat pipes on the Io. So heat pipes is that this Stanian lead, so effectively is not moving around the planets, but is ignoring the convective cell, is still hot and fragile. So continuously you have a fracture where you have mantle material that is coming up, and you are evacuating heat and magmas, and so is the satellite Io, and so you have this widespread volcanism. And then you have here for Venus and Mars, two other processes of three, mantle plumes, delamination, and instabilities. Here is too small to read, but we will see this in the next slide. And from this, probably only planet Earth go here, plate tectonics. And I will define plate tectonics for this lecture to have this subduction like today. Okay? So what is the tectonic processes with the Stanian lid in Venus or on Mars? This is processes that we have, at least the first, well, all three, but the first two is mostly concerning Venus and Mars. Also today on our planets. Sorry, this is in French, but sometimes I found a nicer French diagram. The generally never happens. It's always we go on American textbooks to find, but we are changing, so we have something nice. Forget this subduction zone. Ignore this. Imagine that you don't have this. This is the lamination. What is the lamination? You have a part of the lithosphere, a slice, like a bacon slice, that is separating from the rest of the lithosphere. And so you make the part of this crust lighter. So by isostasis going up, and so he can fracture because it became more fragile. So you can have volcanism, you can have orogens, and you have this part that is plunging down in the mantle. The lamination you have today on the Earth, you have a lot of places where we can show some orogens, local orogens and volcanism due to the lamination. So for some reason and force, you break this slice, horizontal slice. For this reason we call delamination. We take off a sheet of the lithosphere. This is Rayleigh-Taylor instability drips. So you have cold lithosphere that start to be unstable, go down in the hot asthenosphere, that is the hottest part of the mantle, and part of the mantle is coming up. You can reproduce this in laboratory. I read in one of paper, just mixing olive oil and water, but with the price of olive oil water is probably to better something different. So two density different liquids, and you can produce this, and this part of hot mantle is coming up. Maybe at the time it was some generator of local mantle plumes. We have this on our planets. We call the mantle avalanche, and we have this in the past, and we have evidence also today with the tomography that we have this mantle avalanche also in the mantle. The most interesting one is having mantle plumes, were probably present any times. Comatites come from mantle plumes. So all the comatite is 3.5, in Canada is 2.7, the Aleppo comatites. This is comatite from the Komati Gorge. Comatite is not a name of mineral, it's the name of a small river, Komati River, that is in South Africa, and this valley is all 3.5 billion years old comatite where has been discovered. And mantle plumes today on our planet produce, well, highland like Hawaii, that is very nice, but also what we call oceanic plateau. And this is very important because the first continent was probably oceanic plateau. So let's look at this in the next one. So this is a map. So what is an oceanic plateau? Oceanic plateau is that when a mantle plume hit oceanic crust, or you have a localized magma that pour outside the oceanic floor and create island like Hawaii, or you can have large, very thick, from 8 to 35 kilometers. The oceanic crust is normally 5 kilometers. Oceanic plateau. So you have flood basalt, like the Deccan Traps in India, your colleague from India, that is on continent, but you have also on the oceans. The biggest one is the Ontong Jawa, is cover maybe 1/3 of the Pacific Oceans. And so you can create very thick crust. And this is very important because this is probably is the first, let's say, continental crust. Continental just because probably arrived to the surface outside the oceans. But it was made like the oceanic crust of basalt, okay? But it's very interesting, this hypothesis, because it was thick, still very hot, sitting on a very hot mantle, and so inside you have sufficiently heat to have magmatic differentiation. So you melt a part of this basalt and you produce a liquid more silicic, so a more, we say, differentiated, our geologists. And this is probably in these felsic rocks that you find these old zircons like Jack Hills. So you don't need a modern continental crust to have Jack Hills zircons. All the Hadean zircons is probably come from this pocket of melted rocks that change in chemistry or something that looks more like granites, let's say. And so it's easier to find zircon in granites than in basalt. You can find in basalt, it's very rare. You probably have to spend weeks and months in your laboratory to find one granite in some tons of basalt. So it's more classic to find in what we call differentiated rocks like granitoids. And it's also interesting, this hypothesis, to have this first continental nuclide make of this oceanic plateau, because the roots, again, are so hot that you melt the basalt, and when you melt the basalt, you form the TTG. It's not the only mechanism. I will show the other mechanism that has been developed and modeled by Hervé Martin and his student, Jean-François Moyan, that you saw yesterday. This is the TTG. This is a silicic, more differentiated rocks that is representing the most of the continental crust in the Archean time. So we are speaking of 3, 3.5, 2.5 billion years, etc. So the most is produced around 3 and 2.5 billion years, but we have, like in Canada, the place at 3.5 or even older, and probably the first mechanism, simple, is to melt the roots, basaltic roots of the oceanic plateau, and the liquid produce TTG. A TTG is a tonalite, trongemite, granodiorite, is three names of evolved more silicic rocks. With the assemblage of these three rocks is the continental crust at that time. So the next question is, when did the plate tectonics begin? Is the title of this small paper that you can read, Geologica Today. It's a very simple one. So if you want to have, if people are interested, I can send, or maybe if you have a site, I can put general papers about all these stories. And if you don't believe what I'm telling, fortunately Jean-François is not here, he has an appointment by Zoom. Archean subduction factor fiction. This is Earth and Planetary Science annual reviews. So Jean-François Moyan knows better than me about this. And so you can check all about a review of the different theory. I will pick up some theory because I remember since I started with Muriel at the schools of astrobiology, always students from physics and chemistry, etc., came to me and said, finally geology, they can explain us what really happened. We do poetry as geologists. You do science because you have to respect physics law and mathematical laws, but we are free to invent anything. So you have to tell me the truth. I cannot tell you the truth, but it seems that geologists know the truth. So what is the evidence of plate tectonics and when? This is a long list. I will not go through all this because I think if I have to start to explain to a student what is a bonanite, I don't know if it's in the list, fortunately not here. It's a rocks that you find normally in subduction area in volcanic arcs. It's from the Bonan Peninsula that is in the volcanic arc of Japan. I will stay 3 hours to explain. But let's see the most important evidence that today we use to understand there is plate tectonics and subduction, especially because we decide that subduction is the key for the life, probably, or reducing the atmosphere, or exchanging matter, or recycling elements. So on all this list, the things are very important. Forget the 4.4 billion years of continental crust based on the Hadean zircon. I just show you that you can have Hadean zircon in a crust that is completely not like a modern continental crust. But if you look at the numbers, except the 2 or 3 outlier, we have a magic number that is around 3 billion years. So I will use it to explain why we think that is a 3 billion years that start, let's say, plate tectonics. Maybe not really the modern one, but that is a big problem because if it started 3 billion years ago, how we eliminate the runaway Venus-like massive atmosphere? This is an interesting question. So if you want to do a PhD thesis on that, you have time to change your subject. Okay? So I will speak about eclogite, paleomagnetic evidence of continental drift. So this plate movement on the surface, blue schist, and continental crust again. So let's go to continental crust. This is a complicated diagram, but forget all this curve and concentrate on this first 1, 2, 3, 4. So this blue one and this in red. This is what we think is the models based on isotopic. I will explain on the right how we calculate this. This is the volume of continental crust in percentage of the surface of the Earth that has been produced from time zero, 4.5 billion years ago, up to today. And what is interesting to see here, that when you arrive around 3 billion years, you have like a tipping point, and you see we are going rapidly building continental crust. At 3 billion, maybe we have already 75% of the total volume of continental crust that we have today, and then slow down. And the idea, all models, the model change a little bit, but all models. And the idea, and is between 3 and 2.5, but more or less this. And the idea is that in the first part, we mostly built the continental crust, and then modern tectonics, plate tectonics, subduction start. And so you build the continental crust, but more effectively you destroy crust by subduction. And so we slow down the construction, because in reality we continue to construct crust, but now more efficaciously we are destroying crust. And so this is the idea why we have this change in slope. Okay? How we do that? With the several isotopic system, the most used now is this system, the lutetium hafnium, measured in zircon again. What is happening with this system? You have lutetium 176 that produce hafnium 176, and you have a stable hafnium isotope. This is 177. You can forget the numbers; it's not really important. But what is most important then? These stable isotopes prefer when you have a magma, you start to produce crust from the magma. These prefer to go with the crust. The lutetium prefer to stay to the mantle. So the ratio of 176, 177 hafnium is not increasing or is decreasing with time with the crust, but is increasing in the mantle, because what is producing these isotopes like to stay in the mantle, in the liquid. The others go into crust. And so we measure in 1,000 this work, I think they pass through 20,000 zircon, etc. We can calculate from the number of zircon of the period, the volume of the continental crust, and using these isotopes, we can calculate how much continental crust has been produced by the mantle. And so we constructed this curve in times that say that in the first 2 million, we built a continental crust, and then we start to destroy with the subduction. So this has come this magic number that all geochemists are stopped around 3 billion years to have tectonic plates. Before, probably, we have a Stanian lead situation. How we can see how if the continents are moving, what we call the continental drift. Today we do, one way we discovered that plates was moving, it was to do paleomagnetism. So you know that the Earth have this magnetic field that is very important for life. If not, bacteria will be not there, especially humans. Sometimes you have inversion of this north and south magnetic field, but this is not important. What is important that you can record in the rocks the position and the intensity of the two pole, magnetic pole, because inside the lavas, for example, or even in sedimentary rocks, you have small iron minerals like magnetite, that is like a small complex. When you frozen the lava, this small complex that is the magnetite is freezing in the position following the force line of the magnetic field. And so give you what it was the position of the pole in the past. And the people you start to use this in the 50s, 60s, paleomagnetism. It was a new discipline at that time. And then they discovered that if you stay in two continents, you have what we call the apparent polar wander. So it seems like the pole of the magnetic field is moving through the Earth. And if you stay in two continents, it's move following two trajectories. This is completely apparent because it was not the magnetic pole that it was moving, it was the two plates that was moving. And so your position compare the pole, it was changing with time. And this way we discovered that the plate was moving, and we can reconstruct, for example, the America was attached to the Eurasia, etc., when we have Pangaea 200 million years ago. So it's not the magnetic field, it's the continent that move, so the position compare the pole is changing. We don't have this apparent polar wander for the first period. There is people now that have measured magnetic field in the zircon. Again, Hadi zircon is a very recent paper this year on Nature, of course. Strange things always you publish in Nature. And that say that it was a Stanian lead that you never move. But it's very complicated because you are measuring the magnetic field in tiny crystal. Yesterday you saw what is a zircon. So it's a very complicated story. But here we have a work that put together, again, I think a database of 30,000 paleomagnetic measurements done in the world. And it shows how the Laurentide nucleus, so this is Quebec, not only Quebec, but let's say the old North American continent, move between 2.850, I think, the starting point it should be 2.650 around here. How it move on the planets up to 800 here, no, 700, 600, 500 is the Cambrian. So this is not the magnetic pole, it's like this continent move. And what is very interesting that it seems that, so at starting 2.8, we see that the plates move again, so we have probably modern-like plate tectonics. We start to have subduction, we start to see plates moving. What is interesting here, you have these three moments at 2.5, 800, 1400, where you see it seems like the continent is moving very, very slowly, more or less on the same place. And so the suggestion is that, yes, we have plate tectonics, but sometimes we have episodic Stanian leads. So we still, the mechanism is not completely well lubrified. We have plate tectonics, but sometimes we go back to situation that the plates mostly is immobile like Stanian lead, and then start again to accelerate and moving. So we have still a model is in between Stanian lead and modern plate tectonics. Another way to see if we have subduction for us geologists is always to look to rocks. We start from rocks and then we build the stories behind. And so when you have subduction like today, so you have this plate, this is going down back to the mantle. Along the plates you have rocks that is changing, we call the metamorphic rocks. A metamorphic rocks do not change his chemistry, but he changes his texture. He can change the texture of his mineral, but not the chemistry of his mineral, because it is affected by increasing temperature and pressure. And you can imagine that when you have a plate that is at the surface, it starts to go down at hundreds of kilometers under the mantle, you increase the temperature and you increase the pressure of along the plates. And so you have different places with different rocks, what we call the metamorphic stability field or metamorphic facies. And there are two very important. The blue schist here, that is called blue because contain two minerals that are blue, lawsonite and glaucophane, for the fun. Probably you will forget the name in 3 minutes. But just a blue is very nice. Probably you have, if you have a kitchen with a blue marble, because you think that you have a marble in your kitchen, but you have a migmatite, you have maybe TTG, you don't know, you have a lot of stuff in your kitchen, and it's blue, that is probably blue schist, and you have lawsonite. And then you have eclogite that you recognize for the garnet, this red mineral that is generally rust in your kitchen, so you will not see nicely red. but it will be some point rusty that is garnet, that is a high pressure mineral. So the blue schist represent a high pressure and low temperature field here, and the eclogite represent a high pressure and high temperature. The blue schist is here, the eclogite stability field along the subductum plate is here. These start to appear 1 billion years ago on the record, the eclogite 3 billion years ago. And this is a diamond that is very nice because I'm working now also with diamonds. And that contain an inclusion is a garnet again, is an eclogitic mineral. And diamonds is formed in the mantle, and what we call the eclogitic paragenesis diamonds, we think they is formed close to a subduction plate. In fact, some people say that the carbon is organic carbon that make the diamonds. And this type of diamonds containing this type of inclusion are not older than 3 billion years, while we have diamonds that is 3.5, 3.6 billion years. Again, because the geologists say the truth, dating at diamonds is extremely complicated. So you take the age as it is, but it's not easy, and we have very few data of the diamonds, but we know we have a very old diamonds. So older than 3 billion years, you don't have this type of diamonds with this type of inclusion, okay? So this is another way to see that is probably, again, this magic number. From 3 billion years, we have characteristic facies of rocks that we found along the subduction plate. So I arrived to the last slide of this part, and then I will move to atmosphere. So this is a model of Jean Bédard that is very nice. He divided the plate tectonics in 3 periods. I put again their numbers, but again, we and geologists never believe our numbers. Something around 3 billion years, so a little bit higher, 2.7, 2.5 giga years, and less than 2 giga years. And you have the 3 maybe steps how we move from a Stanian lead to have modern plate tectonics. So the first is the model of Jean Bédard that he speaks about subcretion, that is something between accreting terrains and subducting them, so subcretion. It's very complicated, I don't want to go in detail, but practically he has continental crust and oceanic crust. In a hot mantle, both are young, hot, buoyant, and so you don't have this contrast of densities, and this and they are not cold enough that one, like the oceanic plate, have this gravity force to help the convective forces and bringing them himself inside the mantle. And so for him, during this period, yeah, the plates move, but like I was thinking Wegener, the inventor of the continental drift, and then we developed the plate tectonics. He was just thinking that by isostasy the plates was moving around the planets, but he didn't know, and he had no instrumentation to understand it was a subduction, etc. So he thinks that just the plate move. And a little bit is the same probably before 3 billion years. The plates start to move, but it's like boats sailing this hot mantle, and when they encounter each other, so you have convergent margin, the oceanic crust is too hot and there is too few density difference to be able to subduct under the other, and so just start and then they start to accreting against the other continents. So for the reason the name subcretion. At the base they sufficiently hot to melt apart, and so maybe start to make TTG, but you don't have anything else that is really important happening in this period. So accreting and try to do subduction, so subcretion. It's a very nice model. Contested has all the model because our geologists like to fight each other, like most of the scientists. So, but it's very nice because it's a way to show that some movements start. And then you arrive to what we call the flat subduction. I don't like this name, I will say low angle subduction. This is very important. what is happening is that the oceanic crust is still hot, but a little bit less. And so he starts to subduct. You start to have a density difference between the continents and the crust. The crust is 3.3 today, and the continent is 2.7, the density. So, but at the time less. And they start to go down. So these hot plates are low angle. And it start to increase rapidly the temperature. And this is happening also today in some part of the Andean volcanic arc, so in the South America. And in South America, you have some special rocks that is called adachite. The adachite is the modern equivalent of TTG. If you want to find modern TTG, you go in this place and you have, because some part of the plates, so if you go on the South American side where you have subduction, so you have the Andes mountains, behind you have the S-Pacific rise. Is the most rapid mid-ocean ridge. You produce very rapidly crust that remain hot and buoyant. And so when he's going inside under the South American continent, is going with this low angle. And what's happened with this low angle is go rapidly hot, and you start to melt the plate itself. So you melt basalt. And what's happened when you melt basalt? Now I ask a question like my student in the room. Hervé, what happened when I melt basalt? Because you was distracted. I noticed that. Muriel was very attentive. What happened when you melt basalt? What do you produce when you melt basalt? TTG. This is the model of Hervé Martin and Jean-François Moyen when he was his student. So the adachite have mostly the same chemistry than TTG. There is some small difference, so now the people work on the difference, of course, to say, yes, it was like that, but with difference. But if you melt the basalt, so the plate, the oceanic crust plate, you produce adachites. They have practically the same chemistry of the TTG, so you produce TTG. And this was the model for this period of Hervé Martin and Jean-François Moyen, how to produce TTG. With this plate, they go in subduction and melt itself, producing these basaltic melts that then became differentiated TTG. And then, probably maybe even less than 2 billion years, we have modern tectonics. Again, I give a numbers. It could put 2.5, 2.3, 1.8, who knows? Well, we should know because we know the truth, but who knows? And today you have this plate that go with a very step angle down is very cold and very dense. And so you have this gravity force that help to go down. And what happened today, this is what we call the mantle wedge. You are not anymore melting the slab, but you are just dehydrating water from the sediments that cover these plates. And so you give water to this mantle, and you have 3 ways to make the mantle liquid. Because I say the mantle is not liquid, but we have volcanoes. So it's you lower the pressure, you increase the temperature, or you put the water in the mantle and you lower the melting point. Is what's happening here. You put the water, you're dehydrating the slab, you add the water here, and the mantle melt point go down, and you create liquid magma. They go up and create this magnificent volcanic arc like Japan, Auletians, etc., etc. And so it's the classic modern plate tectonics. You have blue schist, you have eclogites, and the rocks that you form in the arc magmas is not anymore TTG, is andesite. Andesite is in the middle of between basalt and granites. In the middle of this, what we call magmatic differentiation, so the production of rocks with more and more different chemistry is in the middle, exactly. And so today the continental crust is andesitic and granitic composition, completely different from the first crust that was probably completely mafic and basaltic 4.5 billion years ago, 4.2 billion years ago, 3 or whatever you want, okay? So it's probably is a model, but it's very nice because we see this essay or to try to have subduction. If subduction is representing what we call plate tectonics.